Analyzing algorithms. An algorithm is a set of steps required to solve a particular problem. One problem can have many algorithms which can provide the required solution. In such a case, we need to have a method of finding the best algorithm which can solve the problem. So we need to compare algorithms on the basis of time. The faster algorithm is considered to be the better algorithm. In other words, the algorithm which takes the least amount of time is considered to be the best algorithm. Now, an algorithm takes an input and produces an output. The time with which it does so is largely dependent on the input. Let me explain this with an example. So let us consider a very simple search function. What this search function does is, it takes in an array and a number x, and it checks whether x is present in that array. So it traverses the array element by element, checking if the element in the array is equal to x. When the element in the array is equal to x, the search will be successful and the algorithm stops. If the element in the array is not equal to x, the algorithm will proceed to the next element in the array. If x is not equal to any of the elements in the array, the search will be returned as unsuccessful. So let us look at a few cases that this algorithm will encounter. The first case is when x is the first element. When x is the first element, the algorithm is going to check the first element if it is equal to x. This is true, and therefore the search will return as successful. The number of checks made by this algorithm will be 1. Let's look at another case that this algorithm could face. Case 2 is x is not present in the array. So in this case, the algorithm would have traversed through every element in the array, checking whether those elements are equal to x. None of the elements are equal to x, and so the search will be returned as unsuccessful. So the number of checks made by this algorithm is equal to the number of elements. Let us say that array has n number of elements. Then the number of checks, which is equal to the number of elements, will be equal to n. Case 1 here is the best case, and case 2 is the worst case. As you can see, the number of checks in the worst case is much larger than the number of checks in the best case. When analyzing algorithms and comparing them on the basis of time, we are concerned with the worst case. This is because the worst case is dependent on the size of the input given to the algorithm. Also, when we analyze the worst case of an algorithm and we try to reduce the worst case time, we will in the process also be reducing the best case and the average case as well. So it is better to be concerned with the worst case when analyzing algorithms. So when the worst case time goes down, this implies that the best case time will also go down. Now that we are convinced that the worst case time is what we must be concerned with while analyzing algorithms, the question arises, how do we calculate the worst case time given an algorithm? This can be done by counting operations in the worst case. So let's see how to calculate worst case time given an algorithm. We do this by counting the operations taken by that algorithm in the worst case. Before we start counting the operations of an actual algorithm, let's go over a few rules. The rule is that primitive operations such as assignment, any kind of calculations, indexing into an array, and calling and/or returning from a function, all these, which are called primitive operations, these take unit time. Let's look at a few examples and see if we can count the primitive operations in those statements. The first statement is I equal to 3. This takes 1 unit of time because it performs one assignment operation. The second example is array of I equal to 3. This takes 2 units of time. The first unit is for indexing into the array A in position I. The second unit of time is assigning 3 to this element. In this way, we can count the number of operations in an entire algorithm. Let's look at an example of an entire algorithm and see if we can count the number of operations it takes in its worst case. So the example I have taken here is a simple function to sum digits from 1 till n. I'm taking n as my input variable. The first step is I'm going to assign a variable called sum the value of 0. Then I will have a for loop which runs from 1 till n, incrementing by 1 each time. Inside the for loop, I will calculate the sum. And once I'm done calculating the sum, I'll return the sum. Now that we have the algorithm, let's start to count the number of operations. So the first step is going to take one operation. This is one operation for the primitive operation of assigning 0 to sum. So it's one assignment. Now let's look at the for loop. The for loop has three parts. It has an initialization, a condition, and an increment. So we're going to break it up and count the number of operations for each of these elements. Let's start with the initialization. I is equal to 1. This occurs at the very beginning of the for loop and only occurs once. The number of primitive operations in the initialization is 1. And that only occurs once. So we are done with counting the number of operations done by the initialization. Let's look at the other two parts. We have the condition and we have the increment. It is important to note that the condition is checked before the for loop executes and the increment is performed after the for loop is done executing. Now this loop runs from 1 up till n. Therefore, this loop runs n times because it increments by 1 each time. So the number of times this loop executes is equal to n times. So the condition is checked at the beginning of all the n times that the loop is entered. At the n plus 1th time, the condition fails and the access to the loop is restricted. So the condition is checked n plus 1 times. N times when it enters the loop and 1 extra time when the loop access is restricted and the condition fails. So n plus 1 is for the condition. Let's take a look at the increment. So when the flow of control exits the loop, the value of I is n plus 1, and that's why the condition fails. So I has been incremented from 1 all the way till n plus 1. We are incrementing by 1 each time. So the number of increments made from 1 to n plus 1 is n. This is for the increment. Let's look at what is inside the loop. We have one statement. This statement on its own will take two primitive operations. One primitive operation to calculate sum plus I and one primitive operation to assign the value of sum plus I back into sum. So this takes 2 units of time. We have already mentioned that the number of times the loop executes is n times. So the number of times this statement will execute will also be n times. So the time taken in this algorithm by this statement is 2 into n. Now we have come out of the loop and we have to return sum. This occurs only once and takes one primitive operation or 1 unit of time. Now that we have counted operations throughout this algorithm, let's add it up and see the total time taken by the algorithm. So the total time is equal to 1 plus 1 plus n plus 1 plus n plus 2n plus 1. When we take the sum, we arrive at 4n plus 4. This is the total time taken by the algorithm in its worst case. So we can say that time is a function of the input size. And in this case, t of n is equal to 4n plus 4.